Okay, and we are live. Welcome, everyone. I'm Deirdre Longacre Smeltzer, MAA's Senior Director for Programs, and I'm with Michael Pearson, the Executive Director. Hi, Michael.
Hello, good evening. Great to be here again for another one of these lovely online distinguished lectures. I'm really proud of this series.
Me too. I have really enjoyed it. This is our third lecture of the 2023 season, and I just think we've had an outstanding collection of speakers throughout last year and this year, and tonight will be no exception, as we are going to welcome Dr. Laura Tallman in just a few minutes.
That's right.
Yeah.
I've always thought of Laura as exemplary in her ability to pursue all kinds of seemingly disparate interests and nevertheless get so much done. Very much in the MAA spirit of mathematics and adventure and students.
Indeed, I think she's definitely a model of following your interests and doing it really well. So, welcome to everybody who's joining us. If the YouTube chat should be live throughout the event, and if you want to kick us off by dropping in the chat where you're joining from, feel free. We always love to see where our viewers are tuning in from. And we'll be starting in just a few minutes, but I want to highlight that our MAA Open Math program is going to be, for the second summer, offering an array of online summer workshops. They have 7 carefully curated summer workshops that will be delivered by experts in the field. And this is an NSF funded project that allows us to develop these programs, and it's highly accessible because it's all online. So check out the registration link on our webpage. Registration is open through April 19th, so just a couple more weeks to choose which workshops you want to attend and sign up. And MathFest is around the corner too.
Yeah, speaking of registration, early bird registration is open for just another 10 days. It closes on April 15th. So we'll be in Tampa this summer, the first week of August, and I'm already looking forward to that meeting. We got a great program lined up, and you can learn more about that at ma.org/mathfest, I believe, is the right link to go to. So take a look at that.
Yeah, thanks. All right. Well, welcome again to everyone who's joined us. We are going to go ahead and get started with the program. I want to reiterate that the YouTube chat is going to be available throughout the presentation. So feel free to use that as a venue to ask questions or respond to the speaker's presentation. And then we will have time at the end of the presentation for some Q&A with Dr. Tallman as well. And with that, Michael, I will turn it over to you.
Thank you, Deirdre. Hey, Laura.
Hi.
How you doing? Good to see you.
I'm great. It's good to see you.
I was thinking about it earlier today. I don't think I've seen you in about a month of Sundays. It's been a while.
And maybe perhaps more than a month of Sundays. Yeah.
It's been a while. Mm-hmm. But anyway, great to have you here tonight. We're really pleased to have you in this virtual format. You know, you and I have known each other for a while, so I'm thinking, well, who needs to be introduced to Laura? Everybody knows Laura. But of course, that's not quite true. And so just a couple of things and a question or two. So I know you got your PhD from Duke in 2000, I believe it is. And you've been most of the time at James Madison in Harrisonburg since, although I know you spent some time in New York at the Museum of Math and with a maker lab.
It's a bunch of 3D printing companies, but yeah.
A bunch of 3D printing companies. Mm-hmm. So, you know, I really appreciate the way that you embrace all these different interests and yet bring them back to the center of how do they help us deepen our understanding of mathematics and the world we live in, and of course I really appreciate how much you focus on students as well and sharing what you know with other people. So we're going to get the benefit of that tonight. But one of the things that I've noticed you've started referring yourself to as a computational designer. And that's a term that I'm not really familiar with, but unpack that for us just a little bit, if you will.
Well, I did say that I was a computational designer, and if there's any computational designers watching this, I'm just like a fake computational designer. Everything I do is kind of a hack, but I've managed to figure out how to design 3D objects using computational tools, using code. I'm not formally trained in any of that, so I do a little bit of everything, a little bit of every way. Um, but my tools are all computational. Like I don't have like a pile of clay that I can mold with my hands to make art or something mathematical. I can't work with my hands like that. I don't know how, but I know how to write code and I know how to plug away at something until it works. And I think that's what I'm referring to with computational, just that I'm using digital tools to create physical objects.
Yes, yes, yes. Well, experimentation and exploration is the way that we create new mathematics, and it's
Mhm,
the way we deepen our understanding of the world we live in. So
mhm.
I think that's totally cool.
It's a very
And
similar process, the design process and the math process.
hmm
Mhm,
and I am looking forward to hearing more about that. Um, Now, I know you were an MAA Project Next
mhm.
Fellow. You've won the Alder Award for teaching. You've won the Trevor Evans Award and others for writing. You've won teaching awards. So I'm not even going to try to detail all of that, but it's quite an impressive record, and it's just absolutely great to have you with us tonight. And I'm going to turn it over to you
Okay.
and enjoy your talk myself.
Okay. Thanks. Thanks for that
Thank
introduction.
you.
Now, I is let me know when you can see my screen because I think you can see it now. Okay, good. So thank you so much, Deirdre and Michael, for that introduction and for making this possible. What I'm going to talk about today, if I can make there we go. I am going to talk about 3D printing that leads to publishable mathematical results that undergraduates can collaborate with. And the three things I'm going to talk about, you can see them in this. I think you can see my mouse here, these three things right here. Those are the three projects I'm going to talk to you about. Every single one of those projects was a collaboration with my colleague, Steve Lucas, who's pictured here. And he's also at JMU. And hopefully he's listening to this and I do our work justice, Steve. I'll do the best that I can. You can see underneath my picture that I'm more of a pure mathematician and Steve is more of an applied mathematician. If you even believe in those labels anymore, that's how we would be labeled. Um, but both of us tend to do a lot of things, like a lot of things a little bit. And because of that, we found that our interests actually overlap a lot and we could work on a lot of projects together in the context of creating 3D models that help illustrate mathematics. And we're doing this in the JMU Experimental Mathematics Lab, which you can see pictured here. It is an extremely small space. That is actually a panoramic view of the space. So you have to imagine it like folded up into a tiny box. It's like only two people can stand in there and they have to be quite friendly at one time. And so that is where we have students come and work on projects with us and try to realize things in 3 dimensions. You can see at the bottom of this slide here that there's a QR code and a link. Those will go to a copy of these slides, a Google Slides copy of these slides. So if there's ever a link you want, or you want to refer back to it later, or you just want to go back and forth while I'm talking to be on a different slide than the one that I'm on, you can see these slides at that link right there. And I'll also give that link at the end of the talk. Also, I can see the chat here and I might notice it while I'm speaking. And if you ask me a question, I might answer it. If I don't see it while the talk is going on, then we can talk about it at the end. But if you see me look over here, I'm checking the chat to see if there's anything that I should address in the chat. Okay, so I want to talk about these three things. The first thing is try tangentless knots. Now, it turns out that there are some knots that sort of roll around on the table when you put them down because they never have any tritangent planes. Now, I first discovered this, I was first told about this by a colleague who pointed out this paper by Morton that had these parameterizations. And I'm going to tell you why I was even thinking about this. I was working with a student in the Gem Lab, and that we were printing a lot of knots because we were thinking about knot theory. And he said, you know, it would be really nice if we could write a program that would orient every knot so that it sat on the build platform in three places, because then it would print like more sturdily. You really want good contact with the build platform when you're 3D printing. And he said, I want to write this program where we'll be able to orient it before we get it into the slicing software, and then our prints will be better. So I said, great. And I talked to a colleague about this, and he said, well, did you know that there's some knots that they'll never touch the build platform in three places? And frankly, I didn't even believe that. And then he showed me this paper by Morton. It turns out that the trefoil knot, if I understand this correctly, is the only knot that has this property, and there are multiple parameterizations of the trefoil knot that will make that true. So here is, right here on the screen, these three equations. This defines a trefoil knot in space that has the property that there's no tri-tangentless, there's no triple of points that lie on the same tangent line, not even through the interior. And what that means is when you put it on the table, it'll only touch it in 2 points. It also means the knot is going to roll around. Okay. Now, this paper of Morton's, it looks a lot like this slide. It didn't have any pictures in it. It certainly didn't have any 3D pictures in it, but it didn't even have any 2D pictures in it. And no one had actually made one. So my student and I set off to try to figure out how to make these. And this is sort of the end of years of work with different students, but here's where we ended up. I'm going to show you the end first. So here's a video of the end of our work. And you can see it rolls like just barely, like the slightest breeze is going to make this thing roll across the table. It rolls extremely well. It's optimized to do that. Now, the first ones that we made with those equations, they didn't roll like this. They rolled, but they needed to be encouraged a little bit. What Steve Lucas and I started working on with a student who at the time was a freshman, and in fact, two other students, one of whom was a freshman and one of whom was, I think, a junior at the time, is we started looking at how to make these knots roll the best. Okay. And so here's the parameterization again. The first thing we did is sort of normalize everything so that the knots would sit on sort of the same torus envelope so that they were a similar size when we printed them out. We didn't want to print out one that was really long and one that was really small or something. So the inside of the torus is getting bigger and smaller here, but the outside radius of it is sort of staying the same, getting the same feel. Okay, so that's the first thing we did. And then you can see there's parameters in here, like there's a C, which scales everything. There's an A and a B, and the A and the B are related. Okay, so the first thing we did is we started looking at what is actually happening when they're rolling. And this is one of the many things in the talk that was Steve Lucas's idea. You'll hear me say that a lot. Anything that has to do with like a numerical calculation or analysis of what we're doing is probably Steve's purview. So what we did is we looked at a convex hull of the knot. So I have one of those right here. So this is one of those tritangentless trefoils, but I've taken the convex hull of it. So it's like embedded inside this object. And then in MATLAB, divided this up into small triangles so that when you rolled it along the table digitally, you can see sort of how the path of it is going to move on the table. So this is kind of like if you covered it with ink and rolled it along the table, what it would look like. And that black line in the middle shows that the knot is moving back and forth as it rolls side to side. So that's the first thing we looked at. We were looking at how the center of mass changes as you roll it. And it turned out this one is for A equals 0.3. Okay. it turned out that this was not what determined whether the knot rolled well. The knot might have like a, jaunty back and forth walk, but that wasn't what was keeping it or not keeping it from rolling. What was keeping it from rolling was the height of the center of mass, which is changing as you roll it around. So to find out which one rolls the best, you can see in this graph here, we're testing it out for different values of A, of this parameter A. So when A is this large one, 0.9, you can see it's got these huge variations in the center of mass as it rolls. And that's how the knot kind of gets stuck, like it would roll and then it wouldn't want to move anymore. And so the first thing that we did with these students is figured out how to minimize the variance of this up and down center of mass. And then it turned out that this A equals 0.5831 is like the best parameter for doing this. And you can see that the other values, like 0.3, we had 83% vertical movement of that center of mass. Is very bad from center, but for this best A, there was only a 2%. Okay, so that's great. But after thinking about it for a while, we realized that actually we could optimize every A if we just stretched out the knot. So stretching out the knot in one direction can have the effect of taming the center of mass movement that's happening. So we actually figured out that we can optimize every Morton knot for every A if we multiply by some stretch factor. So the one that we found, 0.5831, is just what happens when the stretch factor is 1. Okay. But for every type of knot on every different shape of torus, we could actually make a knot that rolls as much as well as possible. You can see the center of mass variations there are fairly low percentages for all of these different shapes of knots. So all 4 of these conformations of the trefoil knot actually roll very, very well. And I have a video of it. So here's what it looks like rolling on a board. Excuse this table. In our department, we call this the table of knowledge, and it's a very old table. So we love it that way. So here is this one rolling. You see it's very flat, but it does a good job rolling. It's difficult to keep them to go straight. That would have rolled down if we got it straight. There's another one. And then this one, you can see it walks a lot back and forth, but that's not impeding its rolling ability at all. And this thing that we were making here was part of an exhibit that we were putting together where it was like an art exhibit where people were going to be allowed to roll the knots down and try to keep them centered. As you can see, that's a little bit challenging. Okay. That unfortunately was right before the pandemic, however. So we did, with one of the students, we wrote up a paper for Bridges for this, and it got accepted into Bridges, and we were going to go to Finland to present this paper, and we got the rolling exhibit accepted into their art exhibit, which was great. But then there was a global pandemic and we didn't go. So we didn't get to do that. But the paper is here and you can see this paper if you want to online. And actually, I'd like to tell you how to make these knots because you might also like to make knots or other closed curves in space that you can print out and analyze and experiment with. So the program that we use to make the knot models is called OpenSCAD. I say OpenSCAD because I feel like it, but it's really called OpenSCAD. So with OpenSCAD, it's a very simple programming language where you type stuff on the left here, and then what you type determines what's going to be produced in this render on the right, and then that's actually exportable as a 3D printable file. And this whole program, this whole language, is geared towards making models that 3D print successfully. So you could make this in Mathematica, for example. If you make this in Mathematica, it tends to make a lot of internal geometry that's really unfortunate and doesn't print well, but OpenSCAD is really good at managing that internal geometry, and so it's better to make it here. So this right here is the dumbest thing you could possibly do to make this model. All of the code is visible on the screen right now that makes this model. And basically you have a parameterization of the curve that you want to have. And then what I'm doing is making spheres at data points along that curve, and then taking convex hulls of successive spheres, of nearby spheres. Okay. Now, if you know anything about 3D modeling, you'll know that taking the convex hull is a very calculationally expensive operation. It generates a lot of crazy geometry. It takes a long time for OpenSCAD to sort it out, but it will create these. So as you can see, it's kind of very jagged. This is very stupid code, and it produces a very elementary model of a closed curve in space. The next slide I'm going to show you is going to change just a little bit right now. You can see that now the curve is very smooth. And in fact, I could easily make it a lot smoother than this if I wanted to. What's happening now is instead of taking convex hulls, which is very expensive, what's happening is we're using a lot of mathematics in a whole bunch of sort of calculus-based libraries that you can define a cross-section of the knot, of just the path, and then using, you know, tangent and normal vectors and the curve itself, you can actually move that cross section around like some circle or polygon around, and then on the fly create sort of a paneling that connects those cross sections, and you don't have any weird geometry. There's no convex hull computations. It ends up being very elegant and very fast and makes very good models. So I have this, it's kind of polygonal in the cross section here, but I could crank that up and it would still go very quickly. Okay, so if that was interesting to you, you can't see all the code here because you can see by this scroll bar, there's kind of a lot of it, right? We're just looking at a tiny piece. If you want to see it, this is where you can find it. So if you can get the slides for this talk or type in that link right there, at this link, there is a link to a Google Drive of files. And you can see right here, easy not tubify and hard Sweeper self-contained. Those are the two pieces of code that make closed curves in space that are reliably 3D printable. And so you can access that code and use it if you want to make something. Or you could just go to Thingiverse and download some 3D printable models that are already made and print them. These aren't optimized. These are from before we optimize things. If you don't have a 3D printer, you can go to Shapeways and order 3D prints of these objects. And I do recommend using Shapeways for this type of thing because I'll just show you one of them right here. So I think you can see that. It's very delicate and it needs to be very smooth or it's going to catch when it rolls. And I can send you the files for these too if you don't want to have Shapeways print them for you if you have a good printer. But I highly recommend doing it on Shapeways. So you can get your own rolling knots there if you want. So that's work we did with some students, and one student actually helped us to write that paper, and she got published on that paper. Future work, there's other trefoil parameterizations that that we could investigate. You know, we've been doing the best we can to minimize center of mass motion, but maybe we could do better or fix it entirely. I don't think we can actually. A really important thing is all of our analysis assumed an infinitely thin path that's the knot. But of course, when you 3D print something, it has a thickness, right? And that thickness actually can matter. And none of our analysis so far has actually taken that into account. But we could take the thickness into account. And we have tried printing knots of different thicknesses, and it does make a difference to their rollability and which ones roll best, but we haven't done the analysis yet. And then also, you saw the convex hull of that knot. We're kind of curious. This is a video from YouTube. It's not our work. You can see that this oloid, it really is very similar to the convex hull of our tritangentless trefoil. And so we're kind of interested if we can expand our work to this larger category of things like sphericons, other developable surfaces. So there's more work that could be done here, and it's accessible to students, even early students who are early in their mathematical career. Okay, so that's the first thing. I'm looking at the chat just to see if, okay, no questions yet. Feel free to throw something there. I might actually notice it. or we can ask questions at the end. The second thing I want to tell you about, actually, I'm just going to set this little timer here that reminds me how much time I have left before I start talking so that we're not here for 6 hours. I think it would be good if we ended at the right time. Okay, so the second thing that I want to talk about is a project about graphs, not graphs like in calculus, but graphs as in graph theory, but in space. So when we usually think about graph theory, we think about it drawn on a piece of paper. So we're thinking of a collection of vertices that are connected by edges, and you draw that on a piece of paper, and the edges might intersect each other, and we just ignore those intersections because they aren't actually vertices, they're just intersections. For example, you can have a type of graph called a complete bipartite graph. And this type of graph, you have a set of vertices like K33, you've got 3 vertices on one side and 3 vertices on the other side, in this case, the top and the bottom. All the vertices on the top are connected to every one on the bottom, but not to each other. And all the ones on the bottom are connected to everything on the top, but not to each other. And you can make KNMN for any M and N, a set of M vertices connected to N vertices that are connected to the original M. Now, these are famously non-planar. So I say famously because even K33, which is a pretty simple complete bipartite graph, is famous for this thing called the utilities problem, where you have 3 houses and 3 utilities, and you need to hook them up with wires and pipes or whatever. And can you do it without those things intersecting? And the answer is that, on a plane, you can't. Matt Parker actually sells a mug that you can write on with a marker to solve the utilities problem, because then you're technically on a torus. That's really cool. I highly recommend. I don't remember what the name of that store is right now, but if you search Matt Parker utilities mug, I'm sure you'll find it. So K33 cannot be drawn in a plane without the edges intersecting, even if I make them curvy and go everywhere else. And that's going to cause every other complete bipartite graph to be non-planar because K33 is inside it. Okay, so okay, fine. That was some basic graph theory. What does this have to do with 3D stuff? Well, we started wondering, and this is something we've wondered about with students for, I think, maybe 6 years. These are the common ways to represent complete bipartite graphs on a piece of paper. Is there a best way to visualize them in 3-dimensional space? Like a lot of what we do in math, it's an artifact of the fact that we all write on paper with a pencil or a pen. If we could easily work in 3 dimensions for these, is there a good canonical way to make graphs like this? They're called spatial graphs because they're in space. And so we started a long project with many, many students who are just starting out in math. Each year, a different student would contribute a little bit to this project to find out what are some of the best ways to arrange graphs in space that sort of reveal their core properties and also are aesthetically pleasing. Okay, so for complete bipartite graphs, we have some pretty good, cool answers. So if you look up in the top there, you can see that picture of K85, again, complete bipartite graph on 8 and 5 vertices. And all 4 of these things spinning around is also K85. That first one that's spinning in the upper, I think you're seeing it on the left, but the first one that you're seeing there, the 8 vertices are around the equator, and the 5 vertices run up and down vertically. And all the ones in the center are connected to everything on the equator, but not to each other. And all the ones on the equator are connected to everything in the center, but not to each other. It's a beautiful representation. And the student that figured this out, he did not even tell Steve and I that he had figured it out. He didn't think it was important. And I was just looking through like the folder where we keep all this work, and there was this OpenSCAD file in it, and this was in there. And it's fantastic. What a wonderful way to represent K85 in 3-dimensional space. And if you look at the second picture, that's like K58. Right now the 5 goes around and the 8 is up and down. The 2 at the bottom, the first one at the bottom, you've got 5 vertices and 8 vertices in a line, each in a line and connected. That's sort of, in a way, the most sensible thing you might ever think of to do. And then the last one is kind of like a combination of these. It's 8 in an arc and 5 in an arc that goes the other way and connected. Now, we were really interested in making these not intersect, have the edges not intersect. That's a pretty trivial problem with spatial graphs, because you can always just, jiggle things around. If they happen to intersect, you can make them not intersect. But it's less of a trivial problem when you want the edges to be straight. So we wanted straight edge, non-intersecting, structure revealing graphs of these. So this is generalizable. Every single one of these ways of representing a complete bipartite graph is generalizable to any m and n. So what about other infinite families of graphs, like complete graphs? So a complete graph is what happens when you just connect all of the vertices. So if you have 8 vertices, you connect every single one to every single other one. That's a complete graph. Now, K4 there, I've drawn it so that it intersects, but if I took one of those diagonal ones on the inside and drew it in a curve around the outside, I could draw it so that it lies in the plane without intersecting. But everything after that is non-planar. There's no way to get it to not be non-planar. So we wondered, can we do the same thing that we did for complete bipartite graphs for complete graphs? And the answer is sort of. So here's K4 and K5. K4 has a lovely representation in 3 dimensions. It is a tetrahedron, and there's no other thing that's possibly going to beat that. I mean, that's amazing. K5, since K4 is inside K5, we thought about adding a vertex to K4. So here's 3 ways that on the bottom here that we could add a vertex to K4. We could add it in the middle of the tetrahedron and then connect it to everything. We could add it on one of the edges, I think is on the outside. We could add an extra vertex that's outside of the tetrahedron and kind of cone it down onto all the other vertices and connect. Or we could put the extra vertex on one of the faces of the tetrahedron. I don't think any of these is any better than any other one. It's not really a canonical way to do that. And you may already be suspecting that there's not going to be a nice general solution for all Kn here. But I do want to explore what kind of solutions students came up with for various values of n. Okay, so for example, K6 is lovely as an octahedron, as you can see there in the first spinny graph. Now that self-intersects. I'm really not as concerned about that here because I just want to find a nice way to represent these complete graphs. If they intersect, it's actually not so bad because you can see the structure. But if it bothers you, you can do the second graph that's spinning around. That graph is the same as the first, but with the vertices kind of just jiggled out of the way just enough so that the edges don't touch each other. And once again, our edges, when we 3D print these, they're going to be actually have a thickness. They're not going to be infinitely thin. So you have to give them a hefty push when you jiggle it. The third one, the twisted prism, is one of my favorites that a student came up with. This picture doesn't do it justice. And for some reason, I don't have a copy of it in my hand, although I do have K44, which is really cool that I can show you later. But when you actually see this model, it looks so simple. It doesn't look like it could possibly have enough complexity to be K6. It was one of the first really nice graph models that any of our students had come up with. I just love that. It's actually the logo for the Gem Lab now, is this twisted prism. And the last one, we thought we could be really clever. And one year we thought, you know what we should do is place the vertices randomly on a sphere and then maximize how far apart everything is, in particular how far apart the edges are, so that we can get nothing to intersect. And it comes out I guess it is a twin. I don't know what an antiprism is. Someone in the chat said twisted antiprism. Maybe you're right, or maybe I don't know. Maybe Steve. But the last one. We thought we'd be so clever and that it would be some beautiful thing, but it's just horrible. So this is like an optimal one, but like from a design perspective, it's terrible. I mean, you can generalize that to any end, but it's just not very nice. It's great though. K7 is difficult because of the 7, but K8, some interesting things start happening again. Like you have this hexahedral conformation here, has a high degree of intersection, especially in the inside, right? But I think it's worth it, frankly, because it's so nice to see this structure in there like that. But K8 is also, 8 is also twice the number of vertices in a tetrahedron. So we could take a tetrahedron and put another tetrahedron inside it, so its vertices are in the centers of all the faces, and put our K8 on that. And that actually works very well. It also has some self intersections, but again, you can jiggle it if you want to for that one that's at the end there, and then they would not intersect. So these sadly don't generalize to KN, but it still was a fun investigation to figure this out, and many students contributed to thinking about those things. Okay, so what other graphs could we possibly look at besides complete bipartite graphs and complete graphs? Well, one of the most famous graphs is the Peterson graph. It's right here in the upper right with the numbers on it, and it comes up a lot in graph theory. This graph, and we saw online somebody else had already made a spatial representation of the Peterson graph that we just adored. It's this first one right here with these numbers. Again, a tetrahedron, and you just put a dot and a vertex in the center of every edge and connect everything up. And believe it or not, that is the Peterson graph. It's lovely that that's the case. I never would have expected that. Now, of course, this self-intersection here is not really a vertex. So if you wanted to, you could move these extra vertices along their edges so that the inside doesn't have an intersection. If you care about that, you can do that. Okay. Now, these have numbers for a reason. You're going to find out. Okay. We're going to come back to this. So it turns out that the Peterson graph is part of something known very reasonably as the Peterson family of graphs. And the Peterson family of graphs is a set of graphs that you get from K6, our friend, the complete graph on 6 vertices, everything connected. If you take K6 and you do things called delta Y and Y delta moves, you get new graphs. So this little picture here in the corner, one looks like a Y and the other one looks like a delta. A Y delta move is you identify a cubic vertex like that, like the Y, and you replace the center degree 3 vertex with a little triangle. So now you have 3 vertices instead of 1. And a delta Y move goes the other way. You identify a triangle and you shrink it down to a point. Now that makes a new graph. That does not preserve your graph, but you can sort of generate a family of graphs by doing these operations, and you get these 7 graphs called the Peterson family of graphs because one of them is also the Peterson graph. And they have a cool property. It turns out that this set of graphs, 7 graphs, I think if I'm remembering this correctly, we'll find out on the next slide, is just sort of like the forbidden set of graphs that you don't want to have in your graph if you want to avoid linking. Okay, so it turns out that all 7 of those graphs, which I am going to show you in a minute, I'm just putting it off for a minute, all 7 of these graphs are what's known as intrinsically linked. No matter how we draw them in space, K6, the Peterson graph, and the other ones in this family, they will always have 2 disjoint cycles like this that are linked. Okay, so no matter how you embed it into space, I mean, you can always take a graph and put it into space in a way that makes a link in an unfortunate way, but I'm saying you can't avoid it. They're intrinsically linked. Not only that, those 7 graphs, no minor of them has that property. So they're sort of like the smallest bad thing that can cause a link. And if your big graph has these forbidden graphs in it, then your big graph has to have a link. Okay, so these are very important in graph theory. And here's 2 ways that you might see it depicted in the literature. I just took these out of 2 papers that were talking about this Peterson family of graphs. Now, from these pictures, it is not clear to me what is the delta Y or Y delta move that's even happening here. Like, where are they? And I can't even tell which one is the Peterson graph at first. In the second one, it's very difficult to parse what these are. And one reason that is difficult is because we tend to draw graphs on paper in a symmetric way, as symmetric as possible. And then that is actually hiding the structure and the relationships between these things. So we thought, what if these were in 3D though? I mean, are they related in a more like tangible way that we can see? So we started, again, we have some students working with us, and we started by really picking apart what this family is and how they're related. So here we're tracking, we like to start from the Peterson graph and end up at K6. I think usually people start at K6 and go the other way, but we like to start with the Peterson graph. And then that Y delta 1 means we're doing a Y delta move on the vertex labeled 1. So that vertex labeled 1, which is currently a Y, is going to get turned into a triangle. And if you track through these things, you can track through exactly what's happened. Now, this is satisfying because you can see kind of what's happening, but it's not, it's still not very clear. And then, and again, Steve Lucas is a genius because he's the one that noticed this, okay? If we make these into 3D models the way we were thinking about with the Peterson graph, this is what they look like. What is happening when you do a Y delta move is you're cutting off the top of that tetrahedron, and then you're cutting off the side vertex of the tetrahedron, and then the other side, and then the back side across the top there. So this is amazing. So you can actually see the Y delta moves. You can see there's a Y on the top that turns into a triangle, a delta, and that goes all the way across. Those are the Y delta moves. And then the moves that go down to the other two, those are kind of unfortunate. We're really not sure how to put them in the story, but the top one, at least, this is amazing that you can see this. And here's a GIF of it so you can see it happening. So this is the Peterson graph turning into K6 with Y delta moves. I mean, this is now just crystal clear what's happening with the structure here. I think this is my favorite thing we've ever done, because it's so clear compared to the two-dimensional pictures. You really see the utility of why you might want to think about this three-dimensionally. Okay. So we got this published in the Journal of Mathematics and the Arts, and there were probably about 7 different students whose work went into this, but those students didn't write this paper and put it all together, so they're not listed as authored there, but they're listed in the acknowledgments and talked about in the paper. And every one of those students had like a little contribution along the way. And these students were often freshmen or sophomores considering being math majors. It's really important, I think, to get students involved in research early if you can. We also made this website here that I'm not going to click on it, but you can later if you want to. On this website, you can actually look at the 3D visualizations of all the graphs we studied. You can download 3D printable files, or you can order prints already done by Shapeways if for some reason you just have to have one of these graphs. And as more students come along and work with us, we can add more types of graphs to this. There's lots of directions here that we could go with. I think what we're going to continue with is thinking about intrinsically knotted graphs, which is sort of the same kind of idea as intrinsically linked graphs, except the graph has a knot in it instead of a link. Everything else that's actually in this list is stuff that students of ours have already thought about at one time, including the Shikanda graph that's here at the end. I think that, yeah, that is the Shikanda graph. He did an analysis of how that graph is related to the Rooks graph. These two strongly regular graphs with sort of the same coefficients, but they're different graphs. Another student of ours went on to do a graph theory REU and think about Earth-Moon graph colorings. These are all things that we could jump on onto in the future for more work with students. Okay. Somebody in the chat said, "Oh my God, I hope that was about the Peterson graph to K6, because I just think that is the best." Oh, Jonathan Gearhart, is that you? This is Jonathan Gearhart's graph. He's in the chat right now, and he's the one that made this graph. Yeah, hi. Oh my God, we'll have to talk later. Thank you for saying that. Okay. So the third thing I want to talk about is 3D printing chaotic attractors. And Steve Lucas and I did this work together as well, this time with a third collaborator, Evelyn Sander from George Mason University, who her line of research actually is dynamical systems. So she is definitely the expert in this group of the three of us that were doing that. This particular project started because we were really inspired by the art of Philippe Put, who made these beautiful pictures of chaotic attractors. Now, these are not 3D models. I know they look like they are, but these are actually 2D renders in beautiful lighting of 3D objects, but there's no 3D object to print or export here. This is all like maybe it's ray tracing. I don't know what he did exactly, but these are just 2D pictures and they're so beautiful. And we thought, we want these. Like, we want to actually have these in our hands. Like, how can we make these and 3D print them? Okay. So, now, first of all, it's not that hard to 3D print these if they don't get too complicated. So we want to print these attractors where we're following this point as it moves around in space with a tubular path. Mathematica can easily solve systems of differential equations to create solutions that then it can tubify and export as STL. Okay, but as we've seen, sometimes Mathematica doesn't do the best job for something that you actually want to 3D print in real life. And in particular, sometimes with these chaotic attractors and other dynamical systems, there are parts of the model that are really curvy, and those parts are really hard to model. And you can't just like crank up the number of points you use, because then you could end up, needing way too many data points and overwhelm your software or your printer. So we did something that we call the mixed curvature method. And that starts by taking a solution to a system of differential equations in MATLAB, because that's what Steve usually uses. And this example we're going to show you first, that I'm going to show you first, is not a chaotic attractor, but it's this autocatalytic system has this cool property that the X and Y have like a high degree of oscillation as things are working out. And so there's a lot of complexity in this model, and a place where things oscillate a little, and then a place where things oscillate a lot. And it's very hard to 3D print this. So this is actually the first dynamical systems model that we tried to print. Now, if you take the solution that you get from Mathematica or MATLAB, what you get is you can get output that's like equally spaced in time. Like for the t variable, you could take a data point for every, whatever increment in time you're going in to get your data points. But time is not the same thing as space, and the way the curve gets traced out in space may happen kind of at different speeds. And so then you can get longer and shorter pieces, even though you're chunking up by time. So we added this extra differential equation to take care of the length of the curve, the arc length as it goes through. And now we have points that are equally spaced in space. And this is what happens. So here is that, we call it the wine glass. Here's that autocatalytic system here. And you can see that this is with 3,000 points. You can see that the stem here, we did not get what we were supposed to get, which was a tiny little corkscrew like this. This is 3,000 data points connected by lines to make this. And it turned out that in order to get the stem to operate successfully, we would have needed, it was either 30,000 or 300,000 data points. It was a lot, and enough that by the time you tubified it, you would have a mesh with like over 1 million triangles. And that gets into the territory of things that Shapeways won't print, your slicer won't slice, your 3D printer doesn't know how to handle. Okay. So we needed to find a way to make our model better. This is not a way of solving a differential equation better. That part is sorted out. This is about how do we sample the data in such a way that we can actually create this object. Okay. Now, in this case, we could just focus on the stem and increase the count there, but in general, the curvature variability might happen all over the place. Okay. So here's what happened. So this gives it away, but I'm going to say first that we tried to do it basically, theoretically, like we tried to use the actual curvature of what's happening in three-dimensional space. Steve tried to do that numerically. I actually sat down with a pencil and started trying to work it out by hand. It was terrible. Anything like that, it's just way too complicated to do by hand. And nothing that we did could really detect where the curvature problem actually was. Now, in all of my collaborations, I'm always the one that says the dumbest thing. Like, can we just do this really dumb thing and maybe that will somehow work? And that is actually what solved the problem for us in this instance, which is this. We have a bunch of data points. We know where things are bad. They're bad everywhere that when we connect them by lines, the angle is too high. We don't need to compute curvature. We already have a discrete set of points. We just need to go through them in triples and calculate these angles. And if the angle is too sharp, we'll add more data points right there. And we'll do that all over the whole model and then take a second pass. And if it's still too sharp, we'll add more data points right in that spot. And we can really easily, quick and dirty, go through the whole thing and add the data points where we need it to be. Okay, so and it worked fantastically. Like, this is one of these times that the stupidest thing was the best thing. And so here's what happens on the left. You can see us adding points, and if you look at the stem of the wire, the wine glass, and the curvy parts of the base, you can see that that's where the points are being added. And we started with 1,000 data points with just like 4,000. Oh, there it is, 4,035 data points. We got a great model where you can actually see the structure. And so here's a picture of what that actually looks like in a mesh. On the left, we have the Mathematica output, and on the right, we have the output from our mixed curvature method. And you can see that we have a much more regular, equally spaced in space situation with extra points added in exactly the spots we need them to be. And this means we can 3D print it. So we sent this one out to Shapeways too, which is like a 3D printing service, because we needed their $50,000 3D printer to print this, and we don't have one of those in our tiny lab, and it worked. And then our work with Evelyn Sander, we actually recreated the Felipe Put idea of having all these beautiful realizations of these attractors. This is ridiculous because these are also just pictures. These are photos, though. These aren't renders. These are actual photos. And if I was there with you, I would hand them around to you. So for example, here's the Langford attractor. This was printed on a standard filament printer using a standard Mathematica output. So it's a little choppy. It doesn't have to be choppy like this, but it couldn't get too fine, I think, without doing our mixed curvature method. Maybe this one could, because it's the curvature doesn't vary too much. Here we printed this one in the GemLab on our Formlabs printer, so we have a little more detail, but it's still, we didn't crank up the accuracy too much. Here is one printed at Shapeways using our mixed curvature method to make a very accurate model that can be 3D printed and captures both high and low curvature areas. This photo, by the way, was by Edmund Harris, who took all of the exceptionally beautiful photos that you're about to see against like a colorful background. So here is the Ruckledge attractor, same thing, using our mixed curvature method and printed at Shapeways. This is the Rossler attractor. You get just the most amazing things, and so if you ever come to visit me, I will put them in your hands so you can see them, because that's kind of the whole point. Here's the Anashenko attractor. And they're very beautiful, and we've also like sort of, made the lines thick enough so that sometimes they touch on purpose, so that makes it for a more robust model. Here's the Arnioto attractor. This is one that was printed from Mathematica, the original method, and printed on a desktop printer. Here's that same model with the mixed curvature method and printed on the fancy printer. This model actually ended up on the cover of the notices a couple years ago because our article was in the notices that time, and I guess they need pretty things to put on their cover. So this is Edmund Harris's great picture of this model ended up on the cover of the notices. And there's a lot of future directions to go here too. I am not going to discuss these because I am not the dynamical systems person in our group, but there's, except for this one at the bottom here, where you have this varying parameter that we've managed to capture using a 3D printer filament swapper that creates stripes. That's actually a cool intersection of 3D printing and math that happened there. If you're interested in this project, we've made all the code available. Evelyn Sander has it available on her website. You can get the Mathematica code, STL files, MATLAB code, OpenSCAD code, all sorts of things if you're interested in making these kind of objects yourself. And I want to just acknowledge, to give thanks to everybody that helped with all these projects, but most especially to these student collaborators. So almost every one of these students was a freshman when they worked with us. Not all of them, but many of them were freshmen when they worked with us. If we only give undergraduate research opportunities to the 3 best people in our abstract algebra course every year, those are the people that already made it through all the hurdles. They're already interested in math. We need to find undergraduate research projects that are tractable for students who are just starting out, where they can find a way to think about mathematics in a research, playful capacity while they're stuck in a calculus class. Not that that's not also great, but I really believe that's the next thing that we should be thinking about, is this early undergraduate research. A lot of people are thinking about that now. And so I just wanted to put a pitch in for that. Thank you. Here's the link, and here is my website and email. Thanks.
Thank you, Laura. That was really a lot of fun. So let me just remind the viewers that this is the time for Q&A. So if you have questions or comments, or if you saw something that you produced in the talk, by all means speak up by way of the chat, and we'll get to that in just a minute. I also want to remind people that because this is on YouTube, this will be available for future viewing as well. So if you want to view it again, want to pass it on, share it with students, feel free. It's available for future viewing. And we are going to continue to have upcoming distinguished lectures. And so if you have an idea for someone who would be a great speaker that you would love to hear, please feel free to send that to us at programs@MAA. So let's see. I think we already have, we have a comment from Ryan.
I can see already that Ryan, Kristen, and Jonathan, these are all former JMU students who awesome. I haven't seen in a while. And I'm really happy that you're here. And I'm so glad that you're here.
That's great. Well, your talk really was, you called it a tour of 3D printing. It really was a tour. It was very interesting to sort of see the different types of settings that you worked on 3D printing with. And I'm curious, do you have students that you are currently working with? What kinds of projects are you working on right now?
Well, yes and no. The pandemic kind of stopped everything, and then the lab moved into my house because I couldn't be at the office, and then I didn't have any students then, and we couldn't work with students. And then, when time passes, all your equipment breaks down. So we've spent the last year or so repairing everything, get everything to work again. I think in the fall, we're going to finally be ready to have some research students. We did have one group of students that worked on stick knot conformations and finding the vertex coordinates for minimal stick knot configurations that had a thickness, and that was pretty great. They were all freshmen, and there were 17 of them at once. So that was actually really exciting, and they presented their work at VSU and made a poster about it. But other than that, we haven't had the opportunity to do much in the past few years, but we hope in the fall we will.
So yet another toll of the pandemic.
Yeah, it's been rough getting back on track.
Yeah. Well, how do you who comes up with the ideas for the students? Is it you? Is it the students? Is it a combination?
It's so Steve and I have a pretty good set of research questions we can ask students right now. And it's typically not the students in our case because the students are beginners.
Mm-hmm.
So they don't know anything about
Right.
what they could possibly ask. And so our job is to identify things where students can actually participate and have ideas about it, even if they've never thought about that thing before or know what that thing is. And so
Mm-hmm.
it's definitely up to us to come up with like sort of these micro projects that students can get involved in. And then sometimes students stick around with us for a few years. Like
Yeah,
Jonathan ended up doing some amazing stuff with 3D printing.
that's great.
Yeah.
I see we have
Mm.
a question, a wondering from Annalisa
Hi, Annalisa.
about.
Oh, shadows of the knots and graphs. Now that's interesting. Like, 'cause some of them, there's something I didn't put in the talk, but that is in our graph theory paper, which is that we did generalized Peterson graphs, which are like, they have like a star-shaped type of formation, but more polygonal stuff around the outside. And with those, we actually did that. Our goal was to make the shadow be the graph that you're familiar with. So they were like these unravelings of the graph into space.
Mhm.
And so we did think about that in that particular case. But yeah, that's an interesting thought, is like, how can you just sort of like unpack, unstack, a graph
Mhm.
to add
Mhm.
that third dimension? Yeah,
Mhm.
it's a cool idea.
A lot of creativity coming out in these work with these graphs.
Hmm.
Um, yeah, so let me put out, I guess, a last call. If anybody has a question or comment for Laura before we wrap up, um, we've got a little bit more time before we close, but not seeing anything. I will thank you. It was fun to see your great talk, and it was fun to see your fan club showing up in the, in the chat there. That was
Oh, well,
great. So
thanks
thank
for
you to the
inviting
audience.
me.
Yeah.
It's cool to
So
do a talk remotely so that like people from all over can show up to it. That's really amazing. Thanks
it
for making
is.
this opportunity
Yeah.
possible.
It is one of the things we love about doing
Yeah.
the distinguished lectures virtually, is that people from wherever can tune in.
Mhm.
So
It's very cool.
thank you once again, Laura, and thank you to
Thank you.
everyone for joining us.
Thanks.
Good
Bye.
night.